This is ABM 12 Q202 Group 2 presenting the different types of intermolecular forces together with their strength, present in, example, and uses. Intermolecular forces is used to describe the forces of attraction between atoms, molecules, and ions when placed close to each other. Furthermore, these forces hold atoms together within a molecule and exist between molecules.
An ion-dipole force is an electrostatic interaction between a fully charged ion and a neutral molecule that has a dipole. Moreover, it is an intermolecular force that is most commonly found in solutions, especially ionic compounds dissolved in polar liquids. For the strength, ion-dipole forces involve ions instead of solid polar molecules. It has been said that the strength of the ion-dipole force is proportionate to ion charge. It is stronger than the dipole-dipole interactions because an ion has a much stronger charge than a dipole when compared, and even stronger than hydrogen bonds. So for the present in, most commonly found in solutions, especially important for solution of ionic compounds in polar liquids. For example, the example of the ion-dipole interaction is the interaction between a sodium plus ion and water, or H2O, where the sodium ion and oxygen atom are attracted to each other while the sodium and hydrogen are repelled by each other. So for the use in, an ion-induced dipole force occurs when an ion interacts with a non-polar molecule, like a dipole-induced dipole force. The charge of the ion causes a distortion of the electron cloud in the non-polar molecule, causing a temporary partial charge. The temporary partially charged dipole and the ion are attracted to each other and form a fleeting interaction.
Hydrogen bonding. A hydrogen bond is an intermolecular force that forms a special type of dipole-dipole attraction when a hydrogen atom bonded to a strongly electronegative atom exists in the vicinity of another electronegative atom with a lone pair of electrons. Intermolecular forces occur between molecules. The strength of this is that it is one of the strongest intermolecular attraction. It involves hydrogen and an electronegative atom such as nitrogen, oxygen, or fluorine. They are a strong intermolecular force created when a hydrogen atom bonded to an electronegative atom approaches a nearby electronegative atom. Hydrogen bonding is present abundantly in the secondary structure of proteins and also sparingly in tertiary conformation. One example is chloroform. It occurs between a hydrogen of one molecule and a carbon of one molecule. It is used in holding together DNA, proteins, and other macromolecules. It occurs most famous between water molecules. This bond is responsible for crystal structure of ice, which allows it to float.
So let's go on to the van der Waals dipole-dipole forces. Van der Waals forces are weak intermolecular forces that are dependent on the distance between atoms or molecules. These forces arise from the interaction between uncharged atoms or molecules. Moreover, dipole-dipole forces are attractive forces between the positive end of one polar molecule and the negative end of another polar molecule. The strength of van der Waals forces is when dipole-dipole interacts as opposed to covalent connections between atoms within a molecule or intermolecular bonding. Establish attractions between molecules of materials or intermolecular attractions. The dipole-dipole interactions between liquid molecules get stronger as the molecules travel near one another. Dipole-dipole is present when dipole-dipole forces occur between molecules of permanent poles. For molecules of similar size and mass, the strength of these forces increasing polarity. One of the examples of van der Waals forces is hydrogen chloride or HCl. HCl has a permanent dipole. The hydrogen atom has a partial positive charge and the chlorine atom has a partial negative charge. Moreover, the positive end of a polar molecule will attract the negative end of the other molecule and influence its position. Lastly, the dipole-dipole is used if dipole-dipole forces plays an essential role in determining the properties of a substance. They are significant for the formation of stable compounds, including biological organisms. Aside from that, self-adhesives use dipole-dipole forces that allow them to stick onto the surface.
For our London dispersion forces, it is a type of force acting between atoms and molecules that are normal electrically symmetric that is distributed with respect to the nucleus. Subsequently, it is the weakest intermolecular force, and so for each strength as molecule size grow, so does the intensity of dispersion forces. As the atomic radius decreases down the group, the outer electron move further away from the nucleus and because they are the less strongly attracted. Lastly, they are synchronous to create transient dipoles. Furthermore, dispersion forces are present within all molecules, whether they are polar or nonpolar. Also, larger and heavier atoms and molecules exhibit stronger dispersion forces than smaller and lighter ones. And for our example, London dispersion forces is the interaction between two methyl negative CH3 groups. It is also used to describe the spread of bubbles due to the effect of flow turbulence. Though arguments exist on its physical soundness, the London dispersion forces arise from transient dipoles in atoms that induce transient dipoles in nearby atoms, producing an attractive force. Thanks for listening.